So K, the equilibrium constant, is a numeric value that gives us an idea of, at equilibrium, which thing do I have more of, reactants or products? And that's based upon which side of the equation is favored, bringing in energy, bringing in disorder to be able to help explain that. But the K itself is just a numeric value that gives me an idea. When I get to equilibrium, will I have a lot of this or a lot of that? And the equilibrium expression shows how different chemicals impact that. But when we are looking at numbers in a reaction, when we're given a problem, we don't necessarily know, are those the exact molarities or the exact pressures that it would have at equilibrium? So what we do is we evaluate the pressures or the concentrations that it has and compare it to the given ratio, or compare it to the K. When we're doing that, we're doing something called using the reaction quotient. The reaction quotient is the exact same expression as the equilibrium expression. It's products raised to their exponents over reactants raised to their exponents. So it's that same ratio of products to reactants. The difference is when I plug in a molarity, it may or may not be the equilibrium molarity. It may or may not be the equilibrium pressure for a reactant or product. By looking at the values, it helps us to evaluate that and know if we are at equilibrium, and if not, what would need to happen to get to equilibrium. So for this, you do a calculation, you plug some numbers in, and then we're comparing two numbers. Q, our current ratio of reactants to products, to K, our equilibrium ratio of products to reactants. When Q is smaller than K, that means that the top number is smaller and the bottom number is bigger, too few reactants and too many products. The system's not at equilibrium, or else Q would have equaled K. So in that case, I have to get rid of some of these things on my denominator, my reactants. I have to make some more products, which go on the top, in order to get to that correct equilibrium ratio. So we would say our reactants turn into products. In doing that, both of these values decrease, both of these values increase, and they continue to do that until we get to that equilibrium ratio. If we plug in the numbers that we are given and we find out that that value comes out exactly equal to our K value, then that means even though we may not have recognized it going in, the amount of reactants and products, their pressures or concentrations, is the correct ratio of reactants to products for this reaction's equilibrium. When Q equals K, we're at equilibrium. If we do the math and we find out that Q is larger than K, that means the top number, the amount of products, is bigger than it should be for the ratio we're looking at. The bottom number, the reactants, is smaller than it should be for the reaction that we're looking at. We need to get rid of the thing we have too much of, products. We need to make more of the thing that we don't have enough of, reactants, and that will continue to proceed mostly in that direction. In this case, we would say it would proceed to the left until we get to that equilibrium. And at that point, reactants will turn into products at the same rate products will turn into reactants. Whether Q is bigger, smaller, or equal to K, we can expect that reactants are turning into products and products are turning into reactants overall. It is a dynamic process. It's just which one is occurring at a faster rate for that scenario. A couple important notes here. If we started with only reactants, if I had only A and B, I'd have big numbers down here, zeros up there, so our Q would be 0. That would match up with right here, our reactants have to turn into products. It doesn't really mathematically make sense, and we can argue with different math teachers about this. But if I put in just what I would call my products in this case, then I would have a number on top, but the concentrations on the bottom would be 0. A lot of times, math minded people would say that that is an undefined fraction, or we could just say it's a really, really big number. It's approaching or around infinity. None of that matters other than to say that Q is way bigger than K. So if we look at this in terms of maybe a graph and a picture, at equilibrium, there is a certain ratio, and here we have A and B, or of B to A. So when we have the correct ratio, if we look at our K value, there's a little bit more B than there is A. It's slightly above 1. If we look at the initial scenario in this case, we'd see if I put in only A, then my Q value is very, very small. I need to increase that. My Q is 0. I need to increase that. And in terms of the picture, that would be some of the blue turning into the red blue, or excuse me, the red molecule B. But if I had a container where I put a whole bunch of B in and very little A, or maybe I started with only B with 0 A, as described kind of over here, and this graph would continue to go up, well, that is too much of the red relative to the blue. So I need to consume some of that red, make some more blue until I get to whatever the ratio is here. And note that it's not that I have an equal amount of A and B. Right here, I have an equal amount of A and B. I have 4 and 4. 4 over 4 is 1. That is not equilibrium in this case. Equal amounts is not equilibrium. Equal rates. And because of the energy and disorder of this system, it is slightly favored to have a little bit more B than A. It's not possible to draw that perfectly with just these 8 molecules, but once we get to our millions and billions of molecules, we can understand and represent that a little bit bigger. So this graph kind of shows that back and forth idea with knowing that K is kind of in between them. But this right there showing, well, we can have lots of different ratios of products to reactants, only one of which is my equilibrium ratio. So here's a practice problem that has you doing that in a couple different ways, doing the math, setting up your expressions, plugging the numbers in, and comparing your Q's to K.